So we're recording now. Let's begin. So yesterday we had stopped at this point. We were discussing the Box-Jenkins method of model selection, and these two statisticians basically they came up with the whole technique of ARIMA modeling or ARMA modeling. So they identified a three-stage method that you can use to fit ARIMA models, and these are used for forecasting purposes. And as you might have understood already, they are based on autocorrelations in the data. Okay? So how a particular time series might be correlated with its own past values, how it may be dependent on its own past values, or on the past error terms. Okay? So there are three stages to modeling when you're using ARIMA models or ARMA models. So in the first stage, what we do is identification, where you plot the time series itself and then use the ACF to identify the MA order of the time series and the PACF to identify the AR order of the time series. Then in the second stage, we estimate the model. So our goal is to select a stationary model. So in the first stage, in the identification stage, before you plot the ACF and PACF, you'll be trying to ensure that your time series is stationary. Okay? Then after that, you want to select a parsimonious model. So you don't want too many parameters or coefficients in your model, okay? Because although you might get a high value of R square, okay, you'll have too many coefficients and that might not improve your forecasting capability at all. Okay? So in order to select the best fitting model, two criteria are generally used. Okay? One is known as the archaic information criterion, and the other is the Schwarz-Bayesian criterion. Okay? It's also denoted as BIC in some places, SBIC in some places. Okay? So if you come across those terms, they're talking about the second criterion. And in the third stage, once you have selected the best fitting model based on these criteria, which I'll just discuss after this, okay, then we move on to diagnostic checking, where you check the residuals from your fitted model and see if they are free of autocorrelations, okay, and whether they mimic a white noise process. So when we are doing this, what we are trying to see is there any information left over in the data that we were not able to use to actually model the time series? Okay, so by checking the residuals, if we find that they are not mimicking a white noise process, then there is still some information that we have failed to exploit in our time series. Okay, so that will give you an indication that your model is not good enough. You need to repeat this entire process again. Okay? You need to estimate again, maybe change the AR order, MA order, and then estimate your model again, then select the best fitting model based on these criteria, then repeat this process of diagnostic checking. So it will be sort of a repetitive procedure where you keep doing it till you get it right. Okay? So it's more of a process of trial and error. You might not get it right in the first shot or in the first attempt. Okay? So you need to keep trying till you get a model which is sound. So very often people say that the Box-Jenkins methodology of selecting ARIMA models or ARIMA modeling itself, it is more of an art rather than a science. Okay? So you just get better and better at it the more you do it. Okay? The more experienced you become, the better you become at ARIMA modeling. It's not something that you will get right in the first attempt. If you're very lucky, then yes, you might just get it right in the first attempt. Okay? But very often it takes a lot of practice and repeated attempts at modeling to get it right. So we'll just focus on these model selection criteria. I hope more people have joined in. Yeah, I think people are still trickling in. Let's go back. Okay, so the model selection criteria. First, we'll take up the AIC. Okay. So this criterion is calculated this way. We are not going into the details of how exactly we arrived at this formula. Okay, you all can look it up in the references that I give you later on if you're interested. So for the AIC itself, excuse me. Yeah. For the AIC itself, you'll find that this is the formula which is used to calculate the value of AIC. Okay. So in this formula, T represents the number of observations that you've used to fit your model. Okay. Then SSR is the sum of squared residuals, or your residual sum of squares, the same thing. Then N is the number of parameters estimated, which could include, if you have both AR and MA terms, they'll have your P autoregressive coefficients, the QMA coefficients, and a constant term if you have included it in your model. Okay, so if you have the intercept in your model, that will also be calculated when you're computing what is N equal to. Okay. So this is the formula for AIC. Now the formula for SBC is similar, okay, but it's not the same. So here again, you'll see T is the number of reusable observations which you have used to fit your model. Then this is the residual sum of squares. And this again is the number of parameters you have estimated in your model. Okay. Now, if you compare the two, okay, here for any model, what you will find is that as you add more and more explanatory variables, which means if you add more autoregressive terms or moving average terms, generally you will find that the R square of your model increases and the residual sum of squares, that will tend to decrease. Okay. Now our goal or objective whenever we are selecting the model using these criteria is to select a model with the minimum value of AIC or SBC. Okay. So we need to minimize AIC or minimize SBC. So generally what I just mentioned was that if you have more explanatory variables in your model, then your residual sum of squares is going to decrease. Okay, so automatically in both cases here, what you'll notice is that the AIC value is going to decrease, okay, or the SPC value will decrease because the residual sum of squares are decreasing. But at the same time, if some of those explanatory variables which you have added, they don't really have much explanatory power, which means they should not be in your model. Okay? Maybe they're statistically insignificant, they don't have much of a role to contribute in explaining your dependent variable. So in that case, you'll find that because you've added those explanatory variables which should not be there, your AIC value and SPC value will be increasing because N will be increasing. Okay? So I hope you can see the trade-off here. Okay? If you add more and more parameters in your model, it might improve the fit of your model in terms of a higher R square and a lower residual sum of squares. But at the same time, because you have over parameterized your model, okay, you've added too many coefficients which may not really have value for your model. So the AIC value is going to increase because N will be increasing here. Okay. So AIC and SBC both capture this trade-off that is there whenever you try to include more explanatory variables in your model. Okay. Now SBC, you can see that it imposes a larger penalty. Okay. Now, generally, whenever you're modeling, you will be using more than 20 observations for sure. Okay, 20 will be a very small sample, and generally, most people do not use such a small number of observations. So it will be something greater than 20 for sure. Okay, and generally, your LNT, the value of that will be greater than 2 most of the time. Okay, so because of this, SBC imposes a larger penalty if you include more and more coefficients in your model. Okay. So the SPC value will increase by a lot more if you have too many coefficients. So that gives some sort of an advantage to SBC, but again you have to be careful which of these two criteria you use. Now suppose you have a very large sample Okay, a large number of observations. Now, SBC has been found to have superior large sample properties, and it is asymptotically consistent, which means that when you are working with larger samples, generally you might prefer to use the SBC, okay, because it will give you a better idea of what the true model that captures this data generating process is. Now the AIC, okay, it's generally biased towards selecting an over-parameterized model. Okay, because of the fact that SBC imposes a larger penalty, you can see that AIC might be biased towards selecting an over-parameterized model. Now in small samples, AIC has been found to work better than SBC. Okay? So depending on your sample size, you can decide which one of these two criteria you want to use, whether you want to use AIC or SBC. So this will help you to select the best fitting model. Whenever you're doing this repeated procedure of modeling, maybe you'll change the number of AR coefficients, the number of MA coefficients in different models. So to help you to select between the alternate models, okay, alternative models, you can use these two criteria, AIC and SPC. So wherever you find that the value of AIC is lesser in one model compared to the other, okay, you will prefer the model with that lower value of AIC or SPC, depending on which one you're using. Okay, now this is for the last part. Okay, when you're looking at the third stage of uh, the whole Box Jenkins methodology. Okay, how do we actually go about the diagnostic checking? Okay, so the first part is very clear to you. We've discussed it yesterday when we looked at uh, the ACF and PACF. So you might have got some idea of how we are going about doing the identification. Okay, now the second part for estimation itself, once we start doing the practical, you'll understand it. But how to select the best fitting model, that is something that we just discussed. Now we'll come to the last part, diagnostic checking. Okay, so for diagnostic checking itself, you'll be using the residuals from your model. Okay. So what you can do is plot the ACF and PACF of your residuals, okay, estimated residuals. Again, what you will need to see is that those spikes which you saw yesterday in the ACF and PACF, they should not be moving outside those confidence bands or confidence intervals. Okay? So statistically speaking, the value of your autocorrelation coefficients and partial autocorrelation coefficients, they should be equal to 0. Okay? They should not be statistically different from 0. So that is one indication that your model is sound, if that is happening. Then the second thing that you can do is plot the residuals by their standard deviation. Okay? Take the residuals, divide each one by the standard deviation. Now, if these residuals are normally distributed, okay, you can plot it and then you can see if no more than 5% lie outside the band from +2 to -2. Okay? Then you can be sure +2 to -2 standard deviations. Okay, since you have normalized it, that's why you have only +2 and -2. Okay. So if no more than 5% of your residuals which you have standardized this way lie outside this band or bit outside this interval, okay, then you will find that your residuals are normally distributed and you can assume that your model is sound again. Okay? Then the third thing that you can do is use those tests for the residuals that we discussed in one of the earlier classes. Okay, so we had discussed the Box-Pierce test and the Leung box test. Okay? So in those tests, if you remember, what you're doing is taking the autocorrelation coefficients of the residuals which you've estimated and seeing whether a group of them, okay, you're basically using the sum of those autocorrelation coefficients of the estimated residuals and seeing whether a group of them is statistically significantly different from 0. Okay? So if you find that statistically speaking, those group of autocorrelation coefficients have a value of 0, then you can assume that your residuals are a white noise process. Okay? That is the null hypothesis of both these tests. Now, if you reject the null hypothesis, it means that at least one of the autocorrelation coefficients is significantly different from zero. Okay? So in that case, you can understand that your residuals are not a white noise process, okay? The error terms. So that will give an indication that your model is not sound. You need to re-estimate and repeat that whole process till you get a model which is free of all these sort of problems. Okay. Then the other thing that you can do is check your forecast. Now, just because you have selected the best fitting model based on AIC and SBC, it does not necessarily mean that that model will generate the best forecast for you. Okay. So again, to test forecast accuracy, there are certain parameters. We'll probably discuss them in greater detail in the next class. Okay, not in this class, but we'll take a quick look at them in today's class. So generally, to test your forecast accuracy, you can use those parameters and determine which model is giving you superior forecast. So you can also check out of sample forecast, where basically you'll be leaving out some portion of the data when you're estimating the model and then generating forecasts for the remaining time period. Okay? For example, let's say I have 100 observations, okay, and I use only 96 of them, estimate a model using 96 of them, then I generate forecasts for 4 periods ahead. Okay? So once I've generated my forecasts, what I can do is plot those forecasts against the actual data, which is the information that I have. Since I had 100 observations, I still have those 4 observations which I did not use for modeling. Okay? So I can compare the known values of the data to the forecast which I generated and see what are the errors I've made in forecasting. Okay? So wherever you find that your forecasts are more accurate, okay, that will indicate that your model is generating better forecasts compared to some other model. Okay, but it might not always be the case that the best fitting model that you've selected based on AIC and SBC is also giving you the best forecast. Okay, so if you choose one, you might have to sacrifice the other. Okay, but that again is a matter of what your objective is when you're modeling. Okay, so this is just the theory part. Now let's move on to the actual practicals. Okay. I hope all of you have downloaded RStudio.
Yes, ma'am.
Okay. And I had also mailed you all a data set. Okay, so that is something that we'll use a little later on. For now, I'll use one of the built-in data sets that are there in R. Okay. So some of you might be familiar with RStudio. Okay, others might not. So just for those who might not have used it before, I'll probably talk a little bit more about what we are doing exactly. Okay, some of you might be familiar with it, so you might understand easily. But for those who are not, I'll just go into it in a little detail. So if you have downloaded it, I hope you have the latest version of RStudio. Okay, it's called Kick Things. You can check the version number. Now, again, when you're using RStudio, we'll need some packages, okay, that we'll be using. So before we do that, how do you all want to go about this? You all want to do it along with me, or you all just want to watch and then do it for yourselves later?
Ma'am, to do it along with you.
Okay, fine. Okay, so you all can just type. I hope you have opened RStudio. Okay, just type data and these two brackets. Okay. So if you have done that, here in this particular console, what you will see is a list of the data sets that are built into R. Okay. So there are several such data sets which you can use. You need not actually download data from any database. Instead, you can use this to just keep practicing your basic regression, anything that you want to test. Okay, so this can save you some time if you don't want to take the trouble of downloading a data set from uh, one of the databases. Okay, so today what we'll be doing is using this particular data set, okay, air passengers, which has monthly airline passenger numbers from 1949 to 1960. Okay, so this is monthly data. You're already being told that. So we'll use this particular data set today to do our empirical work. Okay, so just type data and air passengers. Okay, so RStudio keeps prompting you once it guesses what you are going to type. So you can just select the prompt. So your work will be a little faster. Okay, so let's select this data air passengers. Okay. Now this is monthly data, all right, on air passengers. What you can do is if you want to check what your data looks like, you can just type air passengers itself, but you can also type head air passengers. Okay, so this will give you the first few numbers. Okay, in your data set, what are the first few numbers for airline passenger numbers? Okay, I believe that the data is in thousands of units. I'll just check that again and confirm. But this will basically give you the first few numbers or first few set of observations. Here you've got the first 6 observations. Okay, now if you want to see the last few observations again, you can just type tail and air passengers again. Okay. I hope you're doing it along with me. If you want me to pause or slow down, you can just let me know. Okay. So if you typed tail air passengers, you'll get the last set of numbers. Okay, probably the last 6 observations. That is what you're seeing here, okay, in the output. Now, if you look here, R has updated the information here and it's telling you that you're looking at a time series, okay, which has 144 observations from 1949 to 1960. Okay, the same information's here. Now let's just try and see in greater detail what this data set is. Okay, since it's coming from R itself, what you can do is just type question mark. Okay, and air passengers. Okay, so I'll just go back a bit. So just look at this. Okay, it'll probably be popping up on your screen itself, so you can see it on your own screen. So this says the classic Box and Jenkins airline data, which gives you monthly totals of international airline passengers from 1949 to 1960. Okay, so this is probably data that was used in that book published by Box and Jenkins, or it is used widely to estimate ARIMA models. Okay, so that's why we're using this particular data set, because it will help us understand very clearly the whole process of modeling. Okay, so just type question mark and air passengers. Okay. Now what you will see on the right hand side of your screen is just a description. Okay, you can go down and it will show you the code and all that which has been used. Okay, so this is very detailed code. We don't need to use all this code because there have been several other developments. So the code is far simpler now. Okay, so it's telling you it's a monthly time series in thousands, and the source is from that particular book that I was talking about. Okay, George Box and Jenkins. Okay, so time series analysis, forecasting and control. It's from that book, which basically laid out the entire methodology for ARIMA modeling. Okay. So now you've seen in greater detail, it is monthly totals of international airline passengers, and it's in thousands of units. Okay. Then let's just take a look at, since we want to follow that entire procedure that they laid out, okay, the 3-step procedure. So let's take it stepwise again. Okay. Before you do that, you might just want to look at some details about this data itself. So you can just type summary air passengers. Okay. So if you type summary air passengers, it will just tell you what is the minimum value of the observations that you have, what is the maximum value, then what is the mean of your data, what is the median, and so on. Okay, so it's just summarizing, some summary statistics are being presented for you, which will help you understand your data itself better. Okay. Now next what we need to do is load certain packages into R so that we can then go ahead with the rest of the procedure. Okay. So those of you who haven't already installed these packages, what you can do is go to tools here. Okay, it's at the top of your screen. So go to tools, you have install packages. Okay. So here you can type the names of the packages that you're going to install. Okay, so you'll have to install at least 4 to 5 packages. So I'll list them here, and those who haven't got the packages installed already, you can install these packages. So you can install ggplot2, then I'm typing it out for you so you can keep installing these packages. Okay. Okay, so when I'm putting this hash here, it doesn't implement that code. Okay. It doesn't run that particular code. So it's just some sort of a description of what I'm going to do. Okay, so those who are installing, is anyone installing these packages or do you have it installed already?
Ma'am, we have installed few, but few we are installing.
Okay, so just let me know once you've finished installing them.
Ma'am, if we have to install, we have to remove those hashtags. Is that what you're saying?
No, don't see, if you have to install, just go to the top of your screen. You have tools. Here you have install packages. Once you click on tools, you get install packages as the first option. There, just type the names of these packages. For example, I'll type, if I want to install ggplot, I'll type ggplot. Okay. It prompts me, so I can select ggplot and say install.
All right, ma'am. Thank you.
Ma'am, there is an error will is coming when we are trying to download the stats package. It's not the full name of it, right?
Can you just repeat what you said?
If we are downloading stats,
Yeah.
there are 5 options, but none of them is like stats. Only stats. There is stats 19, stats expression, stats somat, and stats R.
Uh,
So which one should we follow?
Wait, let me check. Is everyone having that problem? Okay. Fine. What you can do is, instead of using this option itself, just try this.
Mom, tap no, like that work. It will again. It will say an error. Yes.
Mm, okay. What you can do is, don't install that stats one. Just try this command, okay? Maybe you don't need to install it. Just try type library stats and click enter.
Ma'am, but without installing the stats package, how can we use the library code? Like,
I'm guessing that it's already there. It's built into it, okay? Maybe it's a very old package, so it's already built in. These might be newer packages.
ma'am, we can also download it from CRAN, like searching it on in Google stats package, and then adding this package to our program. We can do it like externally, not from
Ma'am,
like.
it is there in the library.
Okay. Yeah, that's why I said just type library and see, then you might not have to go through all that trouble, okay? So let me know once you've installed the packages. Okay, so once you've installed the packages, then just start typing library and the names of those packages which you just installed. Okay.
Can you please explain the stats package again?
Sorry.
Stats package, how did we install it?
See, I think it is built in already. So just type library and then stats in brackets.
Yes, ma'am, I did that.
Okay. Did it load? Did you get any error message or anything? No.
No, ma'am.
Okay, then it's fine. It's loaded.
Okay.
Okay, then just load the other packages also. Okay. Just type library and the names of the packages.
Ma'am, from where can we know the version, our version?
Uh, when you started, right? Is it here? Yeah. Go to the top part of your console when this smaller box on the left hand side.
Got it, ma'am.
Yeah.
Ma'am, so like how can we update it, upgrade or whatever?
If you want to upgrade, then there are packages again which you can either you can just download it again and you can reinstall it.
Okay.
Otherwise, a simpler thing is there's a package called install R. Okay. So
Okay, ma'am.
once you've installed that package, it will appear here at the top of your screen. I've done that for R. So that will help you to update your software.
Okay, ma'am.
Ma'am, I'm getting a warning message as package seasonal was built under R version 4.0.5.
Can you speak a little louder? I'm not able to hear you.
Ma'am, am I audible now?
Yeah.
Ma'am, I'm getting a warning message like when
For
I
what?
type the library seasonal, package seasonal was built under R version 4.0.5.
Ma'am, same thing.
Okay,
We
you can,
need
it's
to
fine, you can
update it.
ignore it. Yeah. When we actually use the command, then if you have a problem, then we'll see to it. But I don't think it should be a problem. Okay. Even I get such warning messages sometimes. You can just ignore it for now. All of you are using the latest version or some other version of R?
And I guess most of us from IBEF are using, not using the
4.0.2.
latest one. Yeah, yeah.
Okay. So for the next practical session, just update your version, okay, to the latest one.
Okay, ma'am.
So once you finish loading all those packages, just let me know.
You're done, ma'am.
Okay.
Done, ma'am.
Yeah, done, ma'am.
Fine. Now for this particular time series, it's already recognized that it's a time series and so on. But just to make our work a little simpler, okay, what we'll do is we'll just designate this time series itself as Y, okay, so that we don't have to keep typing air passengers. It's already a time series, so you need not actually do this. But I'm just doing this because later on for other data sets, it will be useful for you, okay. So once you finish loading all those packages, just type Y, okay? Then this operator and TS. Okay, so you're basically trying to declare that your data is time series. Then type data, which will, you're basically telling R what is the source of your data. Okay? So there you can type air passengers, data is equal to air passengers. Then when is your data starting? Okay? Just remember that it's starting in 1949. Okay, it's given right here. It won't have been there, but basically you'll know generally what data you're using and when it's starting. So it's starting from the first month of 1949. Okay, so that's the information that you're giving R. Then because it is monthly data, okay, you need to specify the frequency of your data. So when you're specifying the frequency, you're just telling R how much time is going to pass or how many periods are going to pass before the seasonal pattern begins to repeat itself. Okay, so here 12 periods or months are going to pass before you see the seasonal pattern repeating since you have monthly data. Okay, so you'll put frequency is equal to 12 and then hit enter. So you're basically just declaring that your data is time series data. It is monthly data, which is beginning from 1949, the first month of 1949. And what is the source of your data? Okay, just let me know once you finish, then I'll move on to the next part.
Done, ma'am.
Okay, everyone's done, I hope.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Then next, what you can do is just plot your time series. You would like to see what it looks like, right? Now, from the summary statistics itself, and when we did head and tail, okay, what you would have understood is that this time series is increasing over time. Okay. Then if you look at the minimum and maximum value, which was there in your summary statistics, again, that is indicating that there's some sort of a trend in the data. Okay? So that is something that you might expect when you're seeing your data from all those numbers that you saw earlier. Okay? So just you can type ps.plot and y in brackets, okay? And hit enter. You can click on this zoom. It will allow you to get a better look at the graph. Okay?
Ma'am, I'm getting an error in it's saying figure margins are too large, and the plot is blank.
Okay, you'll have to adjust your margins. Okay, so what you can do is, I think this is the command. If I'm not sure, you can try this. Okay, you can type maybe 1, 2, 1, and 2. I'm not very sure exactly how this works. It's generally like a trial and error thing for me. Okay. So now plot it. It has, for me, it has increased, but just play around with the numbers till you get a plot which fits the size. Okay, you can probably reduce the numbers, try and make it point. No, try and increase the numbers actually. Yeah, increase the
Yes, ma'am,
numbers.
it
Okay.
worked. It worked.
Yeah. Okay. So you can try this. It'll basically adjust the margins of your plot. Okay, I haven't figured out exactly what is the best set of parameters to use yet. So I usually play around with it till I get it right. Okay. So instead of this, I hope you all have been able to zoom in and also see your data.
Yes, ma'am.
Yeah. Okay. Now instead of this, there's a slightly better looking plot which I really like. So you can also try that. So this just looks better. Okay, it has the same basic information, it just looks a little better. So you can use either one based on your preference. So once you're looking at this plot, what do you all see in the plot? Can anyone tell me? What do you notice from the plot itself of your time series?
Ma'am, there is a trend and seasonality.
Okay, yes. Okay, so the trend, I'm sure everyone will know there's some sort of an increasing tendency in the data. Okay, the numbers are increasing as time passes. So in terms of the long run behavior, you see an increasing pattern to the numbers. Okay, what about the seasonality part? Why are you saying there's seasonality in the data?
Ma'am, in every year, like in 1950, there is a time when the graph spikes up and then it became down. So, and this pattern is followed in every 2 year, like in every year, ma'am, in 1951, in 1952, every time in
Yeah.
between mid of the months, like in after the 6 month, the spike came down, and for the fifth and sixth month, it became a rise.
Yeah, okay. So basically, if you look at this, this is for 1949 up to 1950. Then again, 1950, you see a very similar pattern. Okay. Then if you keep moving upwards this way, it's more prominent here if you move towards 1958, 1960, and so on. Okay. So the peaks and stuff, they look like a mirror image of each other, right? Only they are slightly larger every single time. So here you can see a clear seasonal pattern in the data. In the beginning of the year, the values tend to be low. There seems to be a dip somewhere here, okay, maybe around February or beginning of February or something like that. And then somewhere towards probably the middle of the year or something like that, you're seeing a peak and then a dip again, okay, towards the end of the year. So this is a seasonal pattern which seems to be repeating itself. So clearly you've identified that there are two components in your data which could affect your data. Okay, one is the trend and the other is the seasonal pattern. Okay. Now, because of the trend, okay, can you would you think of your data as being stationary?
No, ma'am.
Okay, why are you saying that your data is not stationary?
Ma'am, because it actually violates the assumption of stationarity of the data. It has the uh, trend and seasonality component. Maybe it has also the error and
Yeah, just based on looking on the data, what you're seeing is that probably the mean is not constant over time, right? The
yes, the
mean of the data is
mean and
shifting.
variance is not constant.
Yeah. Okay. So because of this, it's giving you some indication that your data is not stationary. Okay. That's why we generally plot the time series itself. It tells us a few things about our data which we can use to our advantage to manipulate the data, make it stationary, and so on. Okay. So just a couple of other things to help you understand seasonality itself. Now just remember that for any time series, it has different components, right? You can decompose a time series into 4 different components. You have the trend, cycle, seasonal component, and the random or irregular component. Okay? Now in R itself, they generally tend to, when you're decomposing the series, they kind of tend to club the trend and the cyclical component together. Okay, and they call it trend hyphen cycle. Okay? But just think that you're extracting the trend itself when you're doing this. So when we are looking at our data, after this we'll be doing some decomposition. So when we are looking at that data, what you will be looking at is it's being decomposed into 3 parts. Okay, so one is the trend cycle, we'll just call it trend for the time being. And then you have the seasonal component, and then you have the random or irregular component. Okay? Now, to calculate the trend, generally moving averages are used. So you will have since this is monthly data, maybe a 3-month or 4-month moving average, 5-month moving average, something like that is calculated, and then the trend is calculated. Okay. Now the time series itself, it could be the way that these components enter the time series. It could be an additive time series or a multiplicative time series. Okay. So when I'm saying additive time series, it will mean that this time series is composed of these components where each component is being added to the other one. So you will have trend plus T. Okay, I'll just call it T, S, and R. Okay, trend is denoted by T, S is the seasonal component, R is the random or residual component. So it could enter additively in the time series. So you'll have the time series looking like T plus S plus R. Okay, so the components are being added together and then the time series is being generated. Okay. Otherwise, they could be entering in a multiplicative fashion where T is multiplied by S, which is multiplied by R. So now how to identify based on your data itself whether it is an additive sort of time series or a multiplicative time series, the way these components are entering the time series. Generally, if you notice that the seasonal component, it is more or less fluctuating in the same way around the trend. Okay? For the trend itself, you can just imagine a straight line running through this time plot which you have produced, okay, or generated. Now, if the seasonal component is fluctuating in the same way around that trend line, it means that the time series is an additive time series. The components are entering in an additive fashion. Okay? Instead, if you find that the fluctuations are growing larger and larger around the trend line as time is passing, it will mean that you have a multiplicative time series, okay, because the seasonal component is being multiplied by the trend in a multiplicative time series, right? So the seasonal pattern will keep getting magnified with the passage of time. Okay? So here in this case,
Ma'am,
yeah,
is COVID-19 cases an example of multiplicative pattern?
mm,
Like the cases kept on increasing exponentially, like then the peak,
or
it reached the peak and then it fall.
yeah, I think you can say that, but the problem with this COVID-19 is that the data might not, yeah, that is true for many data sets. It might not reflect the reality because in some places testing might not have happened to the same extent. So even though it's already there, like based on the zero surveys, you'll know that a large percentage of the population has been affected, but still just based on the test results, the numbers might look less. Yes, but you're right. It will be a multiplicative sort of time series. And
Okay,
then
ma'am.
there'll be a dip, okay?
Yeah, yeah.
Okay, so here in this case, it's looking more like a multiplicative time series, right? You can see that the seasonal pattern, it somehow seems to be getting slightly magnified with the passage of time. Okay? Now, again, we'll transform the data. Now, the reason that I'm doing this is somebody mentioned earlier that the variance also seems to be fluctuating quite a bit. So to kind of take care of that fluctuating variance, we'll take logs of this time series, okay? And if you look at the code which has been used by Box and Jenkins, when we first typed that question mark, okay, they've taken logs. So just to replicate that, we'll do that, okay? So we'll just create a new time series ly, okay? Now I'm just repeating what they have done itself so that we can replicate their results. So just type log 10, okay? We are taking logs to the base 10. So we've created a new time series ly where we've taken a log transformation of the time series of air passengers, okay? We've just taken a logarithmic transformation of y. This is to help us kind of reduce the variance. Once you've done this, just plot ly, okay? Let's see what it does. So here you can see that it has somewhat reduced the variance, right? Okay, it has kind of made it more homogeneous. I hope you'll have done this.
Yes, ma'am.
Ma'am, what the log function has done is basically reduce the variance or mean.
Variance.
Okay.
There's still a trend, right, to the data.
Yeah, yeah.
Basically, when you take logs, it will compress the entire data set, right? Okay, so even the mean value now, it will probably be a log of, it will be smaller when you compare it to what you had earlier. It's just a monotonic transformation though, okay?
Understood.
And one more thing to note is that since we guessed that this time series is a multiplicative time series, once we took the logs, what happened to it? Okay. Now the components will be entering additively, okay, in the time series. So by taking the logarithmic transformation, what we've basically done is make sure that the components enter additively now in the time series itself. Okay, I hope you'll have understood this point. Anyone who didn't understand it?
Ma'am, can you please explain it once again?
See, based on the previous plot, if you want to look at the previous plot, just click on this arrow here. Okay. So based on the previous plot, we were guessing that it's a multiplicative time series. Okay, because the seasonal fluctuations seem to be getting larger and larger, which means that this time series y, in that you can write y is equal to the trend into the seasonal component into the residual or random component. Now when I took log of y, I'm taking log of this trend into season into random component, right? Okay. So now because of the logarithmic transformation, it becomes log of t plus log of s plus log of r, right?
Yes, ma'am.
Yeah.
Understood.
Okay, so now we made sure that the those components are entering the time series additively now instead of multiplicatively. Okay. Now next, again, we'll look a bit at the seasonal pattern. We won't really be doing anything much with the seasonal pattern, but it will help you in later work. Okay, so that's why I'm going into it. Now, when you loaded that seasonal package, right, we wanted to produce these sort of plots. Just type GG seasonal, okay, and then type ly in brackets. Now, once you begin typing GG seasonal, it will basically start prompting you, okay, about what you can possibly type over there. Just type ly, then year dot labels equals true. Okay. Just type this and then hit enter. GT seasonal. Just a minute.
Ma'am, it's GG seasonal plot, I
Plot.
guess.
Ah, yeah. Correct. Yeah. Season plot. Sorry. So when you're typing this year labels, true and year, yeah, dot labels dot left. Sorry. Yeah, I tend to get a little confused. So when you're typing this, you're basically trying to make sure that the years are marked on the left hand and right hand side of your plot. Okay? You'll have done this before, is it?
No, ma'am.
Okay. So when you're typing, once you produce this plot, okay, what you will see is the seasonal pattern for each year. Okay. So you're plotting the seasonal pattern against the seasons itself. You can see that they're appearing on the x-axis, all the seasons, basically all the months. And on either side, you have the years. Okay. And for each year, there's a different color which has been assigned. So here you can see what is the sort of seasonal pattern that you're seeing. For example, in Feb, you'll find that there's
It's
an
rising.
increasing trend. Yeah. Okay. So you'll find that there are certain common patterns. Similarly, here you'll find an increasing trend in most of the months. Okay. Then again, most of the time, the peak seems to come here. And then from this point onwards, in August sometime, it begins to dip. Okay. Then again in November, there's a dip and then it picks up slightly towards the holiday season again. Okay. So this is clearly indicating that there's some seasonal pattern to your data, okay, because you can notice a clear pattern for many months. So this will help you identify whether there's a seasonal pattern to your data itself. Okay. Now after this, there's another way to also identify whether there is some sort of a seasonal pattern. You can more or less leave the same command, use the same command, and just type polar equals true, okay, this time. So this produces a polar seasonal plot. Okay. Just type the command and hit enter. Okay, have all of you been able to get this plot?
Yes, ma'am.
Just a second, ma'am.
Yeah. Okay, just let me know once you've finished this.
Ma'am, can you once open that plot?
This one.
Yes, ma'am. Ma'am, how does
Yes,
what
ma'am, done.
numbers are representing? Like, how can we interpret those numbers 2.4, 2.2, and 2.6 like with the graph?
See, here you don't really have to bother about the numbers as such. What you need to look at is the circles itself. Okay. So here, this is probably because of the data we have taken the logarithmic transformation. So it's plotting some points in the data. Okay, it's telling you what the axis itself will look like, but that's not very important here. What we need to focus is on these circles. Now, if they just look like proper circles where there are no dents or anything like that, okay, but instead they are proper smooth circles, that will indicate that there's no seasonal pattern to your data. Okay. Instead, if you find, for example, look at your own plot. Okay, don't look at it on my screen. Okay, look at your own plot. You will see that towards November, okay, where the axis, you can see that portion for November. In every year, you'll see a particular dip over there. Okay. Then again for March, okay, all the circles are moving outward slightly. Okay. Then similarly for May, in the last 2 years, okay, you might not see that pattern, but prior to that, there's a slight dip again in all the data points. Okay, so this is giving you some indication that there is seasonality or a seasonal pattern to your data. Okay, instead of you had nice smooth circles, which is what you'll see in the next data set. If you do this same thing with the other data set that I sent you, you might find that there are smooth circles over there. Okay.
Okay, ma'am, got it, got it.
Ma'am.
Yeah.
Ma'am, as we are moving out of the center point, like as the number of years increases, the circles are becoming less distorted. So, can we say that the seasonality factor is reducing as the number of year increases?
Mm, this plot might not really give you that information, okay, whether the seasonal effect is decreasing, because when we looked at the other plots, that was not the indication that we were getting, okay, from the other two plots. So that's why we use a multiple number of plots to understand the data itself. Okay, so that that might not be something that you can infer from this plot itself.
Okay, ma'am.
Now, after this, we'll just take a quick break. Okay, it's 3:37. We'll take a quick break for 5 minutes. We'll meet at 3:42. Okay?
Okay, ma'am.
All right, can we begin again? I hope you all are back.
Yes, ma'am.
Yes.
Just give me a second. All right. Now let's just try and decompose our time series itself. We won't really be doing anything after the decomposition, okay? But it's just to help you understand the seasonal pattern and so on. Later on, you'll be able to use it when you're working with other data sets. So let's just create a decomposed series, okay? So let's do the decomposition first. So just designate uh, your decomposed object, anything, okay? You can give it any name. Just to make it clear to me, I give it the name ly decomp, okay? Just to indicate that this is the time series that I'm decomposing. Now again, the prompt is there, okay? So you can follow that. So once you type decompose, just type the name of the time series that you want to decompose. Then what is the type of decomposition that you're undertaking? Okay, is it additive or multiplicative? Now earlier we suspected that the time series was a multiplicative time series. The components were entering multiplicatively, but because we've used the logarithmic transformation, now they're entering additively, right? So we can do the additive decomposition now. Okay. So that's what we're going to do. Just type this command and hit enter. Now you won't see any result immediately, okay? But the decomposition has happened. Okay, now let's look at the result of the decomposition itself. Use autoplot and ly decomp, whatever you name that particular object, okay, of decomposition. Okay, let me know once you've finished entering the commands and you have the graph in front of you.
Done, ma'am.
Done, ma'am.
So here, this is the original data itself. Since we took the logarithmic transformation, you can see that it looks somewhat compressed, okay, and the variance is a lot less. Now this shows you the trend part. You can see the clearly increasing trend over time. And this is the seasonal pattern that we suspected from the data itself, okay, that initially there's a dip somewhere around the end of Jan or Feb, early Feb, and then somewhere in August or something, there's a peak. Okay, the same seasonal pattern keeps repeating itself for all the years. Okay, and then once you remove this trend component and the seasonal component, remember the cycle was also captured here for R in this decomposition. So once you remove or filter out those two components, then you're left with the residual component. Okay, whatever you can't explain based on seasonal behavior or a trend. So this plots that residual component. Now again, you can also just type ly decomp. So it's telling you what object it is. It's a decomposed time series. The type of method you've used to decompose it is the additive method. Now, if you look at the data itself, okay, basically it's listed all the data for you. Now this shows the trend, okay, and you can see that every January for every year, you can see that increase in the January values. You'll notice the same thing throughout, okay, for most of the months. There might be one or two odd ones out here and there, but overall you'll see an increasing trend. Okay? Now, if you look at this part, the seasonal part, okay, this is very interesting. So this is what you'll notice, that every January you have the same value repeating itself, okay, for all the years. Similarly for February, for March. Okay, so the same seasonal pattern is repeating itself. Okay? So this is the seasonal component. So every Jan, you can expect that the number of airline passengers, because of that seasonal effect, it's going to decrease. Okay? Again in Feb, it's going to decrease. Then in March, it will increase. Okay, so you see the same seasonal pattern repeating itself for all the years. That's why all the numbers are the same. Okay? And the first thing that just lists the actual data itself. Okay, once we took the log, okay, it's now on a logarithmic scale, so you will see that all the numbers are compressed. Okay?
Ma'am, can you show what you wrote as a code? Like you just wrote ly decom, right?
Can you repeat that?
Ma'am, what did you write to print this? Like just ly decom?
Yeah, just ly decom.
Ma'am, but in my results, it's just coming numbers, like not as a table, like January, February, March. Like it's not coming like that. Just coming numbers without the heading.
Okay, I don't know why that's happening for you. Are you getting at least this random?
Yes, ma'am. I got those random and trend like every seasonal,
Hmm.
but not as like the months. I'm not getting the months and the year.
Okay, I don't know why that is happening. Before that, did you change anything in your command?
No, ma'am. Just the autoplot, ly decom, nothing.
Okay.
Just like
Uh,
following your commands only.
okay, I have no idea. Would you like to share your screen for a minute?
Yes, ma'am. I can do that.
Okay, just 1 second. I'll stop sharing mine.
Like, did anybody get the like my the results that I got, or
No, I got the clear results like the monthly wise and tablish form.
yes, ma'am? I've started sharing. Ma'am, see, it's coming like this.
Okay, your plot looks fine. You can
Yes,
post.
ma'am. It's looking like this,
Okay.
and the results are coming like this, ma'am. And frequency, then,
Decom. Okay. I think what is happening.
ma'am, should I run it again once? If
I think he's
that,
working in the untitled file, not in console. That's why its results is showing in console. So if you write in console only, Rohit, then you can get that.
No, not really. I am also writing in the
ma'am, it,
editor and then the
You, you can
NG
try.
answer in console. But I'm getting the correct answer. Matlab in the table form.
ma'am,
Okay.
Anyone can do some troubleshooting here.
ma'am, it's coming like any. The months are coming as any, I guess.
Uh,
Ma'am, the
it
headings are
looks
not coming. It's coming, but
do okay. Anyone has any suggestions for him?
ma'am, I guess you can continue. I'll look onto it
See,
later. Not sure.
okay, fine. Just stop sharing your screen then. I'll show you one thing. You can try that. I don't know if it'll work. It
Alright.
won't give you the same results that we got, but just try this one, okay?
I think in the definition of 1949, there should be a comma instead of full stop, I think.
In his screen, is it?
Yeah, in his screen. Write
Rohit,
it,
can you,
right at the beginning,
okay,
1949.
Yes, when
When
you're
I was
defining
assigning
why.
y, yes, 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 I did. I gave a full stop.
okay, okay,
So I'll have to run the entire thing again. Okay,
okay.
ma'am.
Ma'am, in the seasonality part, when you were explaining some are positives and some are negatives,
Hmm.
was it with respect to the mean?
No, not with respect to the mean itself. For the entire time series. Okay, yeah, I get what you mean now. Mm, have to get back to you on this. Okay, I'll just check and tell you. I'm not very sure whether it's with respect to the mean or for the entire time series itself.
Okay, okay, ma'am.
Yes, ma'am. That was the issue. Like I gave a full stop and
Okay, great.
the results were wrong. Yeah. Thank you,
Okay.
ma'am. Thank you.
Yeah. Thank you to Mr. Ram Gopal for noticing that. Okay. So another thing which you can do, yeah, you just want to extract one component of it, right? You can just use this dollar sign, and then if you want to look at only the seasonal part, you can do this. Okay. So this will help you look at only one component at a time if you use this command. Okay, now we are not really doing anything after this decomposition. Now there's another way to do the decomposition. Okay, now this is considered the old classical method which was used, I think, in the 1920s or something. So it's not very popular anymore because it doesn't take into account certain other factors like sometimes there are holidays, and so on particular days you'll notice certain patterns and so on. So it doesn't take into account many of those things. Okay, the seasonal pattern, again, you'll notice that it's not very sophisticated. They're expecting that all the seasons will have the same regular sort of feature when you look at the graph, but instead there could be small aberrations or changes here and there. So they don't factor all those things in. So there are more sophisticated techniques which have been developed and which are used widely now. So people use other techniques for time series decomposition and not this old classical technique anymore. Okay? So you can use this sometimes, but you might prefer to use more current techniques. Okay, so the techniques which were used a few years back were X11. So that is another method of ARIMA itself is being used to decompose a time series. So these techniques were developed by I think the US Census Bureau and Statistics Canada. Okay, so these statistical agencies which compile data for the USA and Canada, they themselves came up with these techniques to decompose time series, and you'll find that most of the software have these sort of techniques inbuilt, okay, that you can use to actually decompose the time series. So you'll probably just have to run certain commands like X11 and then decompose the time series, or certain other ones. Okay, so currently the technique which is being used is something known as X13 and seats. Okay, so I think seats is seasonal extraction of time series components or something like that. I don't remember the exact uh, expansion of that acronym, but basically they are methods to decompose a time series into their respective components. So these are the latest techniques. So we'll try and learn those also to decompose our time series. Now, either you can choose X11 itself, or you can choose seats. Seats was developed by the Bank of Spain, and then it was, I think, modified by the US Census Bureau and Statistics Canada. So we'll just quickly look at what are these methods, how do we decompose the time series using these methods. Okay? So when you're doing this, you can name your object anything. Okay, let's just call it decomp. Okay. Now here you're using that seasonal package. Okay, so just type SEAS, then in brackets the name of the time series that you want to decompose. Then suppose you want to use X11. Okay, then you just have to type X11. Okay, and then just type this command. Okay, equal to, in brackets, sorry, not in brackets, you have equal to and these two inverted commas. Okay, just try this command. Okay. So if you've done this,
can you tell what is X11 again?
X11 is basically a technique which is used for time series decomposition. If you want to look up the details, you can go to that US Census Bureau website and look it up. Okay, so basically they use ARIMA modeling itself, but it's quite sophisticated. So they'll be having parameters for even for seasonal, extracting the seasonal component, they'll be making it more sophisticated, fine tuning it so that you get more uh, you are able to capture more nuances in the data. Okay, so if there are certain holiday effects where because of one particular holiday in a season, maybe on one day sales are shooting up or something, it will be able to capture even things like that. Okay. So it is based on ARIMA modeling itself, but the technique itself is called X11. The latest one is X13, but in R you have either this command or you can use seats to decompose. Okay. So once we do this, if you want to get, let's say, let's look at just this. Okay, just type this. This will give you a plot of your original time series and the seasonally adjusted one. Okay. Okay, so if you're looking at this, the line in black is your original time series, LY. Okay. And the red one has been seasonally adjusted, which means that it has been adjusted for the seasonal effects, and you're basically eliminated all those seasonal effects, and then you're looking at the time series. Okay, so the trend is still there in the data, but you're taken care of the seasonal patterns in the data.
Ma'am,
Yeah.
has it become stationary now?
Does it look stationary?
I mean, no.
It doesn't look, because the mean still looks like it's not constant, right? We'll have to test and see. Okay, even though graphically it's looking like it's not stationary, we'll have to test and see. So that's a good question. Okay, so whenever you're doing, once you seasonally adjust, you have to see whether is your data looking very different, has it become stationary, and so on. Okay? But generally seasonality and things, we just seasonally adjust the series and generally then work with it. Okay? That is the standard procedure. For stationarity itself, we usually do things like remove the trend and things like that. Now, I wanted to mention something else related to this. Yeah. Okay, I'll try and recall what it was. Okay. Meanwhile, we'll just do another decomposition. This time it's using seats, okay, which is another technique. So just name this decomp 1. These are again the latest techniques. Okay, so if I just type SEAS and the name of the time series itself, okay, you don't have to type anything else in your commands. Okay, just hit enter. Now this time it's using seats, SEATS. Okay, all capitals. It's using this technique for the decomposition. This is again based on ARIMA modeling, but there'll be slight differences compared to X11. Okay, so this is a more advanced technique compared to X11. So let's try and plot this again. Does it look very different from the X11 result, or is it more or less similar?
More or less similar.
Yeah, more or less similar, but if you just go back a little, you'll see there's a slight difference in the plot. Okay, just keep going back and then come back to this. You'll notice some slight differences there.
Ma'am, is there a process like we can get both the graphs side by side so that it will be easier for comparison? Like, is there a
Uh,
simple way to do that?
Let me try. I don't know. I don't know how well it will work. Let's try. If it doesn't work in this class, we'll try and do it in the next class. Okay. I hope it works. Let's see. Yes. Mm, all right. Okay, I think it has, I believe that it has plotted both. Okay, so one is the orange line is the final from the seats one. Okay, because you can see two lines here, right? One is black and one is orange.
Yes, ma'am. The major difference is near 1951. We can see the difference between two lines.
Yeah, some slight differences are there here and there. Okay, I'll try and perfect this next time so maybe we can see it more clearly. But very slight differences probably between the two techniques. If you want to look up what exactly these techniques are, you can search later. Okay, you can just Google it X13 seats or X11 US Census Bureau. If you type any of these terms, it will come up. Now, from this decomposition itself, you can basically extract different elements. Okay, so final gives you the seasonally adjusted time series. Okay, if you do final decomp, it will give you the seasonally adjusted time series from this decomposition. If you type original and decomp, it will give you the original data set. If you type seasonal and decomp in brackets, then you'll get the seasonal part only of the decomposition, the seasonal component. Okay, and then if you type irregular and decomp, you'll get the irregular component or the random component. So this is another technique which is used for decomposition. Right now, for our purposes, we won't be using this, okay, right now, but it is just useful for you in the future. That's why I taught you this. Now, next after this, we'll examine the stationarity of the time series itself. Okay, we are suspecting that it's not stationary, but let's see, we might be wrong. Now, there are tests of stationarity itself, which are used to test whether a time series is stationary or not. Okay, so I'll teach the theory part next week. Since you all were tired of theory, I thought that it's better to do a practical session today. But this particular test which we are doing right now, it's called the augmented Dickey-Fuller test. Okay, so one of the most popular tests of stationarity is something known as the Dickey-Fuller test. I think I described it to you last time. Okay, when we were, I accidentally, instead of Durbin Watson, I discussed that particular test. Okay, so that is one of the most popular tests. But in this test, it is done to improve the power of the test. Okay, to improve the power of the Dickey-Fuller test itself, this augmented Dickey-Fuller test was proposed. So in this particular test, what you're going to be doing is regressing a time series on its lagged value and the differences of lagged values. Okay, so generally this is done. I'll discuss the theory in the next class. Today we'll just do the test, okay, and it will just help you understand whether the time series is stationary or not. So let's see what happens once we do the test. Just remember that the null hypothesis, I'll discuss the theory in greater detail next time. Okay, for now, it will be enough for you to know that the null hypothesis of this test is that the time series is not stationary or non-stationary. Okay, and the alternative is that it is stationary. So we'll just test this on this particular time series Ly. Okay. Now again, it's giving you the prompt. Okay, what is the alternative hypothesis? Do you want to keep the alternative hypothesis as the time series is stationary, or do you want to keep it as it is not stationary, it is explosive? Okay, so generally the convention is that the alternative hypothesis is that the time series is stationary, and the null is that it is not stationary. Okay, so we'll follow that convention itself. Then K, that other parameter which was being shown, it is the number of lags which you want to include in your test. Okay, so that is calculated automatically, so we need not bother too much about it now. So just type alternative and the particular alternative hypothesis that you're choosing. Okay. So this is a test for stationarity itself, just remember that. And the null is that the series is non-stationary. Okay. what result did you all get? Are you able to reject the null?
Yes, ma'am, we have a smaller p-value, so we'll
Yeah.
reject the null.
Okay. So everyone has got this result? Are you all getting the same numbers or different?
1.01, yes, ma'am.
Okay.
-6. Yes, ma'am. Same.
And it's taking lag value of 5 on its own or what?
Yeah, on its own.
Okay.
There's a basically in the code they have, based on the number of observations and so on, they have uh, basically told R how to calculate the lag order. Okay?
Alright.
So here you can see, because the p-value is very small, we are able to reject the null. Okay, the p-value is 0.01, so we reject the null that the time series is non-stationary, and we accept the alternative hypothesis that it is stationary. Okay, so this particular
Ma'am, but in the diagram, can't we see like there is an increasing trend? So how can the time series be stationary?
Yeah. Okay, so that's why there are more sophisticated tests again which have been developed. Okay, so Dickey-Fuller was one test. Then after that, they found that that was not satisfactory. Okay, Dickey-Fuller itself was not satisfactory. So that's why they came up with something known as augmented Dickey-Fuller. Okay, so with the passage of time, obviously better techniques, better tests will be developed. So we'll do one more. Again, I will not go into the theory in great detail. We'll do this next week. Okay, the theory of these tests itself. We'll try and do one more, okay, which allows us to take into account the fact that this series is showing a trend. That is a good question. So here, this test, it has the opposite sort of null hypothesis. So in the KPSS test, yeah, I'll tell you the expansion of this. It's based on the names of 4 different people. So this particular test, it is having a null hypothesis that the time series is stationary. Okay, and the alternative this time is that the series is non-stationary. So just the opposite of what we had for augmented Dickey-Fuller or the ADF test. So we'll try and test for stationarity using this, because it takes into account the fact that a series might be trend stationary. Okay? So we'll try and test this now. That once you eliminate the trend, the series might be stationary. We might be saying non-stationarity because of the trend itself. Okay, so let's try this. So the first command, first part of your command, it tells you which time series you're testing for stationarity. The second one tells you what are you testing for, what is the null hypothesis, that the series is trend stationary or is it level stationary. Okay? Level means in the levels itself without, what do you say, when you don't, if there's a trend, it means you can remove the trend and then the series will become stationary. Okay, so if it's in levels, that means there's no such effect of the trend itself. Okay? So here we'll test for that the series is trend stationary. That's the null hypothesis. Okay. So this is telling us that, since you can see that the p-value is large, it's telling us that the time series is trend stationary itself. Okay. So once we eliminate the trend, probably we'll see that the time series is stationary. I hope this is clear to everyone.
Yes, ma'am.
Ma'am, what is the null in KPSS test? Can you again
Null is that the time series is stationary. So either it can be level stationary, which means that when there's no trend or anything like that, it is stationary. Okay, but if you notice that your time series has a trend, then it's very likely that once you remove the trend, the series will become stationary. Okay, instead if I had a time series where it was just follow my cursor, it was just moving up and down like this. Okay? So that would be level stationarity. There's no trend in the series, right? There are just up and down fluctuations of some constant magnitude. So that would indicate level stationarity. Instead, if you see an upward trend or a downward trend, once you remove the trend, the series can become stationary. Okay. So in that
Ma'am,
case,
what is the result of KPSS? We reject the null hypothesis.
in this, what we got, since the
0.
p-value is 0.1, it is a large value, right? So you cannot reject the null. So
Yeah,
we'll
exactly.
conclude. So we conclude that the series is trend stationary. Okay.
Okay,
Now
ma'am. Okay.
we'll also check for level stationarity. Okay. But ideally, we should be using trend stationarity because we can clearly see a trend here. So here, when you test for level stationarity, it's telling you that you're rejecting the null, which means that your time series is not stationary. Okay? You're accepting the alternative, which is that the series is non-stationary. Okay? So we'll go with the first result, which is that once you take into account the fact that the series has a trend, that the series is going to be stationary once we eliminate the trend. Okay? So it is a trend stationary series. So how do we get rid of the trend now? Let's try and create a new variable. Now just take Ly itself. Minus, since we could extract the trend from the first classical decomposition method easily. Okay, so we'll use that over here. So let's just go back and look at what we had called the classical decomposition method. I think it's over here, Ly decomp. Okay. Yeah. Okay, so we had called it Ly decomp, so we'll go with that. Okay. So from Ly decomp, choose the trend part of it. Okay. And subtract the trend from the time series. So we're trying to detrend the time series. Okay, let's see what happens. Okay, so we have got this detrended time series now. Let's try and plot this and see what it looks like. Okay, so you can see that now it's looking stationary, right?
Ma'am, then
Yes,
this
ma'am.
will be level stationary, no?
Yeah, now it is level stationary since you removed the trend, no? So now there's no trend in the series itself, so it should be level stationary. So now again, if you want, you can test. Based on the graphical plot, you can see that it's looking stationary. We can test this again, okay? We'll be using the same commands. Now this time, let's choose level. So since you're getting a large p-value, it's telling you that your time series is now stationary. Okay, it is level stationary. Okay, I hope you could follow this.
What does level stationary means? Can you tell again? Like it's normal, it's stationary fully now or some other thing?
No, it is stationary fully in the sense that if you look at the appearance, look at the graph that you have, there's no trend, right, that is visible in the graph.
But isn't there a seasonal effect that is left?
Yeah, there is still a seasonal effect that is left. Okay? That's a good point that you're making, but we are going to model taking into account the seasonal effect. Okay, so we'll try and do that when we are modeling.
Okay.
So if you are looking at a level stationary time series, then it will have this sort of an appearance. Okay, this is of course showing a seasonal pattern, but generally it will appear this way, where the fluctuations are more or less constant and you have a mean reverting series. Now, one thing, just give me a minute. Yeah, if the series is not level stationary, okay, suppose we did this test and we ended up rejecting the null, then what we would have had to do is take the first difference of this particular time series. Okay? So once we would have taken the first difference, we would have had to test it again, which means we would have taken detrended Ly minus detrended Ly at lag 1. Okay? That's what we'd have been doing. So once we took that difference, then we would have had to check if the series becomes stationary. Okay? So if it's non-stationary in levels, then you need to take differences to make the series stationary. Okay? Either the first difference or second difference. So generally in empirical work, taking a first difference usually is enough. It helps you to make your time series stationary. Okay, so here we don't have this problem. We can already see that once we remove the trend, the series becomes stationary. Okay, so this is a trend stationary time series. Okay. Then after this, let's try and model the time series itself using the ARIMA techniques. Okay. So we've already plotted the time series, okay, and now we tested for stationarity. So two preliminary things are done. Okay, so in the identification stage, which is the first stage for the Box-Jenkins methodology, you need to plot the time series itself. Then you need to make sure that it's stationary. So we've done the plot, we've done tests of stationarity, made sure that the time series is stationary. So now we move on to the next part where we use the ACF and the PACF to identify the order of the autoregressive terms and the MA terms. Okay. So let's do that now. So that stats package basically helps you to do this. Okay. So now just type ACF and the name of the time series, okay, that you're using. Here we're going to use detrended Ly. Okay. That is the time series. Then you can either leave it as it is, so it will calculate the number of lags automatically by itself, or you can specify the number of lags that you want to see. Okay, so let's say since we have monthly data, let's take about maybe 12 lags. Okay. Okay, so there are some missing values in the object. Okay, so this generally creates some problems when you're plotting the ACF and PACF. Okay. So let's look at our data once. Okay, so the last few observations are missing now. Okay. So if you remember 1949 also some observations are missing. If you remember what I said when we were discussing the decomposition process, it is done using a moving average. Okay, so obviously some observations will get left out over there. Okay, so because of the fact that you're using moving averages to calculate the trend component, you will have some missing observations when you finally calculate the trend itself. Okay. So to take care of these missing observations, we'll try and look at where exactly they are missing. Okay, so you have them missing for 1949 throughout, I think. No, up to June. Okay, so for the first 6 months, you have missing values. And then for 1960 again, you have, I think, the last 6 observations being missing. Okay. Yeah, so the first 6 and the last 6 observations are now missing. So let's take that into account, and we can again rename our object. Okay. Where we try and take into account the fact that these missing observations are there and we eliminate them. Okay. So let's specify this. Okay. So this is a time series where our data is be trended by. Okay. But this time it is starting in 1949, the 7th month. Okay. And where is it ending? 1960, I think the 5th month, is it, or 6th month?
Well, yes, 6th.
6th month, yeah. Again, it is monthly data. Okay, so we are specifying exactly where our time series starts, where it ends, and what is the frequency of the data again. Okay. So this is our time series now. Let's see if it's the same thing that we're looking at. Yeah. Okay. So now it's just taking into account the fact that you're beginning from the second half of 1949. Okay. So now let's try the ACF and PACF. We'll stop with this for today, and then we can proceed with the modeling in the next class. So the first part, probably Friday of next week, we'll continue with the practicals and then do the theory. So probably at the beginning of the class, I'll cover the stationarity part of it so that you'll understand it better. Then we'll move on to the practicals. Okay, so let's plot the ACF. Again, there are missing values in the object. I'm not sure why.
Ma'am,
Yeah.
can we use is.na and then fill that missing values with the mean of the data set, or like elimination is not the proper thing that we can do. Like it can be done at only the extreme cases. So is that the elimination of the data set, like for 4 year of the beginning and the 4 year of the end, is necessary for?
No, there are other commands like na.omit and all that. So I'll have to look that up. Okay. So basically it'll tell R not to take any action for those missing values, to ignore them. So that I'll look it up in the next class, and we'll probably continue from there then. Okay. So since it's showing missing values, we'll fix that problem and then proceed from there in the next class itself.
Okay, ma'am.
If any of you all want to move forward from here, what you can do just for the next class for yourselves, what you can do is just plot the ACF using this command, ACF and the name of the time series. Okay, you can use this, comma lag.max12. Okay, so that will help you generate the ACF. So then try and identify what is the MA order of the series. Okay, or even sometimes if there are no MA components, you can still identify the AR process also with the ACF. So you can try and do that. For PACF, you'll just have to add a P here. The command remains the same. So you can try that for yourselves and stop for the next class. After that, we'll begin the ARIMA modeling process. So next class, what we'll do is learn how to deal with the missing observations part, and then proceed with ACF, PACF, and ARIMA modeling. Okay? So for yourselves, those who know how to deal with it, or if you take the initiative and find out yourself, just plot the ACF, PACF, and stop at that point. Okay. So we'll stop here for today. Okay. You all can practice using any of these data sets, the decomposition part or anything that you found interesting. Okay. Otherwise, we'll just continue in the next class. All right. So we'll meet in the next
Ma'am,
class next week.
one request, please.
Yes.
Is it possible to share the R scripts you have used? Because my R got hung up in the middle. I missed all the
Okay.
initial script.
Okay. Yeah, yeah. Okay. So I'll do that. I'll share mine, and only thing you'll have to change the path of the file and so on. Okay.
Yeah,
So
that's all.
for the others, those who have done it, you can save your own history. Okay. So you can save the project itself. Okay? And so you'll be able to continue from that point in the next class. Okay. So I'll also try and do that. So let's meet in the next class next week. Okay? Thank you for your time. See you next.
Thank you,
Thank you,
ma'am.
ma'am.
Thank you.
Thank
Thank
you,
you,
ma'am.
Thank you,
Ma'am,
ma'am.
I also had a request.
Yes.
Like, ma'am, while teaching theory, can you explain it with the practicals also? Like, can you do both at the same time so we'll understand better? Like, if everyone agrees, like you are
Yeah.
explaining one, and at that after that, just we can use our studio and do the coding part so we'll understand better.
Yeah, I'll try and do that henceforth. Yeah. Okay, it might not be possible for every topic, like for VAR and stuff. I'll have to do the theory and then do the practical separately. Okay, otherwise it will be too much of a break between things. And so for some topics, I'll do the theory separately and practical separately. For others, I'll try and merge the two so that it's better for you all. Okay? Yeah.
Okay, ma'am.
Also, ma'am, that
Okay,
our
ma'am, got it.
periodical would be an R-based one or a written test. The test
The
that
It's a written test.
so,
Practicals probably we'll do later, maybe after your mid sem or something like that. You'll have a practical test
but
paper.
so right now we have derived everything and that is thing. So, are we expecting question of deriving things or
No, no, no.
practical solving questions?
See, since it's open book, if I give you theory, you'll just be copying whatever's there in your notes. So that's why I said it'll be application based. You'll have to apply whatever you've learned and then write your
Ma'am, if
test.
you have the time
So
and if
maybe
you
you have to
could
solve something.
in the next in the next class, can you just give us some questions for us to practice so as we know what is coming in the test?
Okay, one thing that I need to do is I need to discuss with Professor Kamaya like how we should go about it. So after that, yeah, definitely next week I'll let you know what you can expect from your test.
Yeah, an assignment of some practice question would be great.
Okay, I'll try and do that. Yeah. Okay.
Thank you, ma'am.
And Mr. Ramgopal, I don't know if you're still there. If you would like to take the test
Yeah.
for yourself, then
No,
that
I
would be
think I
great.
would avoid
Otherwise,
that.
okay, fine. All right. But if you're interested in taking the test, you can go ahead and take it.
I guess I'm too old for
Okay.
tests, ma'am.
Okay, fine.
Incidentally, ma'am, last Saturday's your notes could you share again?
Yes, I'll be doing that. Yeah. By tomorrow, you'll get it,
Thank you very
including the
much.
syllabus. I'm sorry I couldn't send it earlier. By tomorrow,
Thank
you'll
you.
get it.
Thanks.
Thank you.
Thank you, ma'am.
Yeah, thank you. Bye.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Welcome.
Thank you, ma'am.
Welcome.